Hello.
Okay.
Hello, everybody. Thanks for coming today. My name is Jasmin Akic, and I'm a member of Salesforce Sales Cloud Performance Engineering team.
Hello, everyone. I hope you guys are having an awesome time at the Dreamforce. My name is Samir Pilipovic, and I'm also a member of Sales Cloud Performance Engineering team. And welcome.
So we have a pretty packed program today, but before we start, I would like to ask you, how many of you are working on analytics of some kind of performance and business trends changing over time?
Awesome.
Oh, that's great, yeah.
Yep.
And how many of you are using machine learning for any of your analysis?
Great.
Okay, good. Yeah, I think this is going to be a good topic for you, right? So today's session was targeted mostly to those who are doing analysis on a time series, performance or business data. That means how particular metric is changing over time. And this might be interesting to people who are working in operations, DevOps teams, admins, performance engineers, as well as developers, business analysts, and consultants. So this session does not require any pre-existing knowledge of any tool. It is trying to explain concepts, but we do provide a lot of resources that we are going to show you after the session, so that if you need some scripts and some guidelines how to implement something like this, what we're going to cover today, you will be able to.
Yeah, we wanted actually to have a full-blown session where we could also show you how to do things practically, but we couldn't squeeze it into Dreamforce. Because of the packed schedule, they only gave us 40-minute slots. So we'll leave it up to you to go and discover the technical side of it. We'll provide everything, so you can enjoy it.
So today, there are going to be two main parts. One part is going to be related to how to actually do prediction on time series data. And once we do the prediction, then how to detect anomalies, or how to detect if something doesn't look right. And also we are going to use Einstein Analytics for the data visualization throughout the session. Our demos are going to cover preparation of input data and actually understanding analysis of the input data, how to find anomalies using predictive models, and how to generate dynamic alerts. And at the end, we are going to hopefully leave a couple of minutes for Q&A session.
Okay.
So this is just a disclaimer that you don't make your financial or other business decisions on a topic of today's conversation. So hope that's clear. Okay. So in today's performance analytics, there are different challenges, and but we could essentially separate them into four different categories. First is how to understand long-term, short-term trends in a data, how to find periodic patterns, what is actually causing these periodic patterns, so that we can take that into account. So once we understand that, we can try to make a prediction. So essentially, everybody is trying to see what is going to be, for example, my sales during the next week or next month or next quarter. Is my technical infrastructure, is my cloud infrastructure good enough to support our business for, let's say, shorter, longer term, essentially for capacity planning? And we would like to see if something is wrong, if something is not as we expect to be. So we essentially try to make a prediction, and based on the prediction to say whether something is anomaly or not. And once we find out that something looks like anomaly, then we need to essentially send some kind of alert. We need to notify someone. So we can try to make a decision whether the anomaly really has a large business impact, does it need immediate attention, or that it is something that can be done in the, let's say, shorter interval after the anomaly occurs. So, and at the end, we would like to, part of the presentation will be related how do we visualize those data, how we show you actual metrics and predictions, and how you could actually build some dashboards using Einstein Analytics and deliver it to other teams in your organization and to executives on a different kind of devices. It could be on a desktop, or could be on a mobile phone, and even on devices like Apple Watch. So this is an example of metrics collected related to some activity. It could be number of, for example, API requests on a system, system utilization, could be number of sales orders or number of hits in the search engine, and so on. But what is important that we can see that data show some kind of periodic patterns, daily or weekly, and we can see even during the day that there is some pattern. We can also, if we look data longer than 1 week, we can see long-term trends. So that if there is a gradual increase, that is another concern that you might consider analyzing. And there are exceptions from typical daily metric shape. So we see that, for example, on Friday or Saturday, the shape is different than it is on Monday, Tuesday, Wednesday, and so on. Sunday also is much different because usually there is no much business activity during Sunday. So, Sami, you want to that one, yeah.
So I'm just going to show you how our input data look like for this exercise. We displayed it in a simple chart, and actually how this whole project started. When we saw it, we saw, oh my God, this looks beautiful. I mean, I hope you guys get excited about data the way we do. But we looked at it like, oh wow, look at this. So as Yasmin mentioned, this is 2 months of data of a particular metric that we collected. And we noticed very interesting patterns there, some periodic and some exceptions. Just please ignore the most right part of it, because that's where we cut off the data, so it looks totally out of shape compared to the rest of the data. And we thought, okay, this looks perfect to do some deeper analysis, and we started playing with various things that we explained, various methods and machine learning techniques to try to see if we can detect something there, that some small delta of useful information that we could use maybe for some more useful things. As Yasmin mentioned, you see the weekly patterns. So basically Monday is always hectic, and then it kind of slows down all the way to the Friday where things slow down. There is one Monday that looks totally different than others, so we thought, okay, this is interesting. And then you have a weekend where things slow down. So it looked great, we liked it, and we started playing with it. So we'll explain in a little bit more details, what we did with it and how we came to certain conclusions. So we just want to show you that. So in essence, humans are still, maybe one day some HAL 9000 will replace us all and do all the, intelligence things, but humans are still, I believe, much better at detecting certain patterns in nature, and we are visual creatures. So, when you look at your data, know your data, try to see if there is something that, looks very interesting that you could use. And I mean, if you have a very random data with a lot of noise, it's probably very hard to detect something useful out of it. But this example was like, yay, look, this is great. We love it, so let's try to use it. So anyways, that's
Okay.
for now for me, so
Okay.
this part.
Yeah. So in order to do prediction, we tried different methods, but one of the simplest ways and probably most effective is simple application of linear regression models to performance data. Could be system performance data, could be other data that you get from the cloud, business related, or even some sales or marketing data. So the simplest linear regression model is essentially just a line, right? Straight line, and it doesn't tell you much. It is mostly like average of the values of the metric that you are trying to analyze. The only thing that you might see is maybe long-term trend. Is it going upward or down or staying flat? So we wanted to see whether linear regression actually can be used to make more sophisticated prediction and try to match the shape of the input data. So since data show periodic patterns during the day and during the week, we tried to see whether we can essentially apply some trigonometric functions, trigonometric features based on a time and make a prediction based on that. So that is a good thing with the linear regression. You can pass to the linear regression not just some variable like time or day in a week and so on. You can pass a function of that value. So in this case, we are passing trigonometric functions, and we see that there is some match, but there is a lot of anomalies, a lot of deviations from the prediction. And then we found out that if we try to use essentially any day or any hour in a week as a variable, which is a binary, we just say whether it is 0 or 1. For example, is it today Wednesday? Is today a holiday or maybe some big event? So these features that could be 0 or 1 actually work very well with the linear regression, and you can make much more accurate prediction if you include even larger number. In this case, we took about 200 different binary values that you collect either from the calendar or from your business. But be ready to use not just the numeric values. Try to put in your algorithms binary features that tell you whether there is absence or maybe there is maybe they show that there is some event that might affect the performance of your system. So, Samir, can you?
So now after we did that, after we went through that exercise, so we tried it with our real input data. So when we applied linear regression using machine learning, we didn't learn much. Maybe it's hard to see, but you can see the curves. The line is, slightly slanted upward. So only thing that we discovered is that, our long term is growing. So whatever we were measuring, over time it's increasing. Didn't really tell us much. So we tried trigonometric method. So we basically passed into our machine learning trigonometric function. So it matched better our training data, but still, there were big discrepancies, and we still couldn't use it really to, make any reasonable predictions or detect some interesting stuff. So we thought, okay, there is a way to do it with periodic functions too, but it requires some heavy math, like Fourier analysis, Fourier transform, and things like that. So, if you have time, you want to do it, sure. But, we said, okay, that's not going to work for us. So let's try something else. And then, as Jasmine said, we sliced our data to as many binary features. Feature is a term from machine learning. We sliced it to as many binary features as we felt needed. So basically, we went to, what day is it in a week, what week in a month, what hour in a day. And then we also had to figure out things like, okay, is it a holiday? Is it a Black Friday? So it depends what you're measuring. If you're measuring some business data, some sales data, of course, there are some important events throughout the year that you have to take into account because it will deviate from the normal patterns of some Tuesday in March. So you have to take that into account. As you can see here on the left-hand side, there's that Monday that was different, which was holiday. I mean, we don't have time to go through the whole process, how we came to this eventually. We realized, okay, we need to get a calendar for this particular org and see what's going on, with this particular metric on different days. So eventually, once we sliced it as far as it goes, you will be able to see that in the code. We were able to train our, use machine learning to train our algorithm to match pretty well the production data. Blue is production, red is our prediction. So as you can see, it's pretty good. There is something in machine learning called fitting your model, so you can, you can go as close as you want. In our case, I believe our model fit like 95% to the real data. At one point, you have to stop because you might overfit your model, and then it basically defeats the purpose. You're cheating. You're going to get wrong information out of it because it's too good. So, but that's a part, in the machine learning theory, you can discover more if you go there. So that's it at this point. So go to the next.
Thank you. So just quickly to go over the machine learning development process. So what you need to do is when you are developing a machine learning model. So what is important and takes really large amount of your time is how to convert input data to a format accepted by machine learning tools. So that you need to collect data from many places. You need to filter them, aggregate them, and convert into format that machine learning tools are using. In this case, we are using Python and machine learning libraries that are supported by Python. But different tools may require a different format of the data. You need to select your feature set. Selecting a feature set is something that we covered in the previous ones. Why did we go from just like time and then maybe some trigonometric features or functions, or could be different. For example, polynomial regression might use like power of a particular variable. But adding new features, new variables to the model is essential part. And then once you collect all the data that you want to pass into the model, you run the model, linear regression or any other model that might fit your data. And then you need to validate the model. Essentially, it is you need to see whether the model works, whether the model is good or not. So you generate some kind of score, and that score tells you how good fit is model with the data that you are providing to it. So it is an iterative process, and then you repeat it until you see that your score is kind of growing. You try to improve the model, and once you see that the score is not going, so there is no better fit of the data to the model, then you can stop that process and say, oh, this is my optimal model.
Or it requires way too much work, way too much slicing of data or molding the data to make even better fit. I mean, you have to make a decision up front, okay, how well I want my prediction to fit my real data. So, it's like, is it 95%, 98%? Maybe for some cases, 70% is fine enough, depends what you're trying to measure, what you're trying to predict, so.
And then once you build a model, you can pass some real data In machine learning terminology, they call it test data, but essentially when anybody who is talking about machine learning, when they say test data, they mean really data that you are collecting, let's say right now, some metric, and then you pass it through the model, you're testing the model. And, but data have to pass the same transformation process. You need to extract these features, and then you apply the model, and you get a prediction. So prediction, applying model and getting a prediction is typically a very quick process in the instant. It is, you can run it in a matter of seconds. So when you collect some metric and then you want to apply the model, it could be done in near real time.
I mean, once you get a code and you play with that, you will see how fast it goes on thousands and thousands of rows of data, very, very fast.
Yeah. Okay. So back to the main topic of today's presentation is how to find what are anomalies and how to essentially generate some kind of dynamic alerts on the data. So if we want to really provide some kind of near real-time notification, what can you do? When you collect a metric, you can say, oh, I can just compare it with the static predefined threshold. Let's say I'm checking my CPU utilization, and if it crosses 85%, it is a red alert. I'm gonna notify somebody that there is a problem. Or you could say if, let's say, number of search hits goes below some record, you can say, oh, there is no activity on a system. What is wrong? Is it a network problem or something else, right? So essentially, we can compare the value and based on if that value is higher or lower than predicted value, we can generate the alert. When we do this, we want to separate noise from anomalies, and in order to do that, so could be just a noise in the data, but could be a real anomaly. And in order to determine that correctly, we also try to derive and calculate something called the prediction interval. So that means, yeah, you predict that, for example, number of requests to the system is going to be, let's say, 50,000 in 1 hour. But you also need to see what is really anomaly. Is it maybe if it crosses 55,000 or it is less than 40,000 and so on. So you need to define interval, min and max value of that interval, and to say, oh, if it falls outside that interval, then we will consider that to be anomaly.
Plus, you don't want to detect something that happens just once. I mean, what we're trying here to accomplish is to detect things that usually stay hidden. You know, if something crashes or there is some big problem in whatever system you're monitoring, that's usually easy detectable. There are many tools that will alert you if your database crashes or you have lots of exceptions or your search goes down or things like that. So we're trying to find things that are normally stay hidden but could be useful. Deliver us some delta, small delta in the knowledge that we can use. And as Jasmine pointed out, we didn't want to detect things that happened maybe once or twice, but it was just, you know, once and twice, and we probably don't care about that. There is some other ways to deal with that. We wanted to detect something that's, you know, happening on a longer period, but it is really deviates from your normal behavior in the system. So.
Correct, yeah. So we want to try to avoid, when building a model, that will cause some false positives and false negatives. So there are methods to apply actually to detect those. And essentially, once we see that there is anomaly, we need to see whether it is higher or lower than the prediction. So, for example, if it is if a metric is actually higher than the prediction, it might cause some system performance problems, so you might notify DevOps team. It might be a business indication that you might need to add more people in your business process to support any activity that you're trying to do, marketing or sales or service. And, but if it is lower, that usually means it is a lack of activity. That is also something that you might notify your team, and so that they can act based on that. So essentially, what we see here on a graph is there is a metric, there is a prediction, and there is a difference between the metric and the prediction. And based on that, we can figure out, okay, is it exceeding our prediction interval window? Okay. So, Samir, you want to show the demo?
So yeah, how does that now look on the real data? So this is now, you know, in a longer session, we would be able to show you the whole process, but this is now our model working against the real data that we feed into the system and pass it through our algorithm. And you can see our model works pretty well and matches our input data. So we went one step further, and at the same time, we have a part of the algorithm that looks for patterns and tries to detect. Yeah, just want to show you here. So this is a Sunday, and this is a holiday, and our model predicted it correctly and didn't show us any false positives or negatives. So back to this, we wanted to see, okay, if there is something, if our prediction deviates from the real data, we want to detect it. You can see here that in this case, on this particular day, our model predicted that the activity should be much higher, but it's not. So we wanted, you know, to know about that. We got this, it's just a graphical representation, and there are a few more places in this whole where it happened here again. Now the question comes, you know, what do you do with that? How do you handle that? In our case, we went for developing a piece of code that will alert someone in various ways. And in our case, we use chatter, so we post a chatter message to, I don't know, your sysadmin saying, hey, your system, there is something wrong with it.
You can see the chatter messages.
So yeah, that's fine.
As a part of the scripts that we provide on a GitHub related to this presentation, you can see scripts that are loading data and manipulating data to be loaded into Einstein Analytics, as well as if you detect anomaly, how to, for example, send a message to Salesforce chatter, or you could send the message via email or any other notification mechanism.
Yeah, you can tweak the code anyway. It's in Python, but I guess it's...
Yeah. So what is maybe important to show here is that it can also detect the opposite when prediction is lower than the actual value, right? So you can, the question is how you want to visualize that, but you actually want to say, oh, these are my anomalies and they require attention. But the question is, how did we actually get these anomalies? For example, here we see that half of the day we have a really lower activity the whole morning than what we wanted, right? So it is a concern. So what we are trying to do is we are trying to define moving average window. So that means that we have a window where data should fit in. And if data, what does it mean is that we don't just look at the current metric, for example, for this hour. We might want to include a number of previous measures. So it could be, let's say, for last 3 hours or 6 hours, and then you say, oh, based on that, it doesn't look good. So that
in this particular case, there was some throttling in the system. Some resources weren't readily available, and that basically all other tools that were monitoring the system missed this. So this is a good way of, and users didn't notice it also because it wasn't like system was crashing or anything, it was just slow. So of course their activity was lower, but nobody was too concerned, nobody noticed it, so, but if this, turns into some bigger issue, you might detect it this way and say, hey, let's go check which of our, parts of our moving system is in trouble or has some hard time producing results. So that's why this activity was lower than expected. It wasn't like people were off. It was just, yeah.
Okay. So just to summarize, actually, what we did for the anomaly detection and how did we use prediction. So we use prediction not only to predict the value. We use machine learning and the models to predict what is the range for acceptable range for a particular metric. So it is kind of a prediction on a deviation that you might see on your data. And that moving window actually has its width and the height, right? So the horizontal size or the width of is a specific number of measures. For example, last 3 hours. Or you might say last 15 minutes or whatever, but could be multiple data points. And the vertical size is essentially what you allow for this metric to have a variation, right? If that metric is exceeding that vertical size, then you declare it as anomaly. So it is essentially a difference between the actual value and the prediction. So what is the anomaly of the impact of the anomaly? It could be that anomaly has a high value. That means that the metric value is higher than the prediction or that lower than prediction. So that comes whether you need to notify somebody, whether you need to just send some chatter message for follow-up, maybe during a weekly meeting and so on. So that means that based on that, you can decide whether the thresholds are big enough to require immediate attention. So you can essentially separate them into alerts and into warnings. So you can also decide which team is going to receive based on the difference between the predicted value and the real value. So once you detect these anomalies and you notify somebody, you might get a feedback back from the business. They might tell you, oh, this is not anomaly. And that's what we had when we found, oh, there is a Monday that didn't show activity that is supposed to be on Monday. Then they said to us, oh, it's a
holiday.
It's a holiday.
It's not in our country.
Yeah, it's holiday in France, right?
It was in France.
We
didn't know. We looked at it like, well, what's going on here?
Might be
Are they on strike or
much lower than should be. Yeah. So you might get a feedback from business and use that information as a feature to improve the model.
It's a continuous process. It requires, might come new things that you didn't predict, didn't think of, but eventually you get to the state where it's good enough to, be useful for whatever you're trying to do.
Okay, so this was pretty much what we wanted to show, but now these are resources that we would like to share with you, and we provided on GitHub essentially a whole set of scripts that you can use to prepare the data, to build the model, to train the model, to test the prediction, to load data into Einstein Analytics for the visualization, and also how to send alerts using Salesforce chatter.
You can tweak it any way you want, so it's open source. So
yeah,
you can use it
there are also tools provided by Analytics Cloud, command line utilities that help you to automate these processes, and we use those in these scripts. if you want to see Einstein Analytics resources, there is a link. And also we recommend that you visit booth for the Analytics Cloud products. And there is another module called Scikit that helps you implement these machine learning methods in Python. So that is for those who are really interested into scripting and automation of all this process.
Basically freely available Python libraries for machine learning.
Yeah, okay. So that would be it.
Thank you very much. If you have questions, please come to the mic.
Yeah.
And
so we'll stay here a couple of minutes and answer questions. Yeah.
Hi guys, so machine learning plus AI, how often are you guys retraining your models? Because it sounds like what you're doing is pretty arduous and maybe manual. In the early stage, yes, there was a lot of, you remember that diagram that shows the loop where you go back and forth until you get it? Well, but once we got the model to work, to fit the data, to the percentage that we decided was good enough, that we could go a little bit more, but it was like way more work than to get maybe 1% better. And actually, knowing what we were measuring, we didn't really have to do much after that because the input data are pretty stable. There are no too many changes in the behavior of the data.
There are events that would cause that. So, for example, you would build a model, let's say, using data from March till June, and then holiday season comes and suddenly your model doesn't work anymore.
That's the tricky part.
Those are the occasions when you need to retrain the model.
I mean, you have to pay great attention to choosing your test data. I mean, training data. So, you have to know the nature of the process that you're trying to model and predict. So,
yeah. So
you might go there a few rounds until you get it right.
There are also some business events that cause that. So, for example, could be a new software release. So you release new software and suddenly your metrics are out of shape, right?
Oh, haywire, yeah.
So they are, that is another reason, mergers and acquisitions. You suddenly add a couple thousand of new users to the system, right?
Okay, thanks guys.
Sure.
So being that we have global systems, did your model consider, how did you normalize the timeout? So was it UTC or because, when users log on in the US, they're normally going to bed in, Western, Eastern Europe or somewhere. So or did you build models based on like time zones? So you use, 4 hours and build separate models because a spike in France might not mean a spike here.
Yeah, this was universal time.
It was universal time, but we eventually had to take into account different calendars. So that was one of the features that we had to figure out, okay, for this particular org, where are they? What are their holidays? What are their some exceptions that might cause things differently? Is it a spring break? So behind the scenes all the times are in UTC, but we have features that tell us, okay, which country it is, where is the org, what time zone, what calendar, and things like that.
Yeah, so for example, business calendars in different countries, those are the important inputs or features that you want to provide to the model. Is it a holiday in France? Is it
Black Friday in US?
Yeah, is it
things are going to be
or is it day after Christmas?
So if I look at like a feature set for for one row, I mean you can be talking about if you're in 25 countries, right? You could be having 25 rows, like 25 columns, features just for holiday yes or no, holiday yes or no, and then you could have a whole bunch of other things on which hour is it in, what day of the week is it in, what day of the year is it in. So was that the way that you guys flattened out? I'll go and take a look at what you've done, but I'm assuming you flattened everything out. So how many features did you have finally for one observation? Because you're doing it hourly, right?
200.
200, okay.
Right. Yeah,
So, okay.
But these 200, about 170 are actually hours in 168 is hours in
it's
a week.
very sliced.
We always essentially check, is it noon on Monday. Noon on Monday is different than noon on Tuesday or Wednesday or Friday.
Okay, so
and they usually show very kind of consistent, behavior.
All right, because another way I was thinking was you can have like a Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, which has, I get 7 features there. Then I have a month feature, it says 1 to 12, and then I have day of the year 1 to 365, and then I can have, every hour. So I have, 24 of those. So that's another way to do it. So
the whole code is.
Yeah, I'll go take a look at it.
I'll take a look, guys. Download
it's a good example. Might be useful for some, might not. You might need to do something totally different. Depends what you're measuring. In our case, it's a time series. So
All right. Thanks.
Sure. Any other questions? We have 0 seconds left. Okay.
Thanks, everybody.
Thank you, guys.